Okay, so this is remediation for Gauss's law. So for Gauss's law, often the most difficult thing is figuring out what the enclosed charge is inside the Gaussian pillbox. So sometimes you'll have to worry about induced charges. This only occurs whenever you're dealing with like nested objects, like this nested sphere or this nested cylinder, where the outer shell is a conductor. If the outer shell is an insulator, then there is no induced charge. Charges cannot move. So let's say the inner surface, or I should say the inner object, let's say whether it's a sphere here or it's a cylinder here, has a charge of Q on it, then that means the inner surface will have a charge of negative Q, regardless of what the net charge is on the outer conductor. The inner surface will always have the induced charge that's equal in magnitude but opposite polarity. Let's say we aren't given the total charge on that inner sphere or the inner cylinder as being Q, but rather they tell us what the surface charge density is. In other words, it's a conductor. So a conducting sphere at the center or a conducting cylinder, and therefore all the charges on the outside of it. And so they tell us what the sigma is, the surface charge density. If you want to know what the total charge is enclosed on that sphere or that inner conductor is, you would have to take sigma multiplied by the area of that cylinder, which would be 2 pi r times the length, or the sphere, which would be 4 pi r squared. Therefore, the inner surface would have the opposite polarity. So negative sigma times the area of the inner object. Let's say the inner object, though, is not a conductor. Let's say it's a insulator. And then instead of telling us what Q is, maybe they would tell us the charge density, rho, and that would be a charge per unit volume. If you wanted to know what the total charge of the inner sphere is, assuming it's a insulator, you'd have to take rho times the volume of that sphere, which is 4/3 pi r cubed. Or if I want to know what the charge contained in this inner cylinder is, assuming it's an insulator, I'd have to take rho times the volume of cylinder, which is pi r squared, the area of its base, times the length. The inner surface would have the opposite polarity, so negative rho times the volume of the inner object. On the outer surface, it's just simply going to be the opposite polarity of this, so it's going to be positive instead of a negative here. And if the outer conducting shell had some net charge, you would have to add that Q net to that. So the net charge of that outer conducting shell plus the negative of the charge of the inner surface. So if it happened to be a negative charge on the inner surface, then it's going to be a positive charge. If it happened to be a positive charge on the inner surface, then it would be a negative charge. Calculating the enclosed charge. Well, if your Gaussian pillbox falls within a metal, so here I have the Gaussian pillbox drawn inside the sphere here. If that sphere is metal, then there's no net charge. Or let's say the Gaussian pillbox goes out here in this outer shell. If that shell is metal, then it would be zero net charge. Same thing for the nested cylinder. If this inner cylinder is metal and the Gaussian pillbox is contained inside that cylinder, inside that metal, then it would be zero net charge. If the Gaussian pillbox is in between the inner and outer surface of the shell, so it's actually inside the metal, then again, the net charge is zero. And if you're like, well, why is that? It's because there's this induced charge on the inner surface that's the opposite polarity of this nested object in the center. And so those two cancel. If the Gaussian pillbox is inside of an insulator, then you'd have to take the sum of all the charged regions. So for instance, it's pretty easy if the Gaussian pillbox is inside, let's say this sphere, and let's say the sphere is an insulator, I would just figure out what that is, and we'll talk about that in a second. But if the Gaussian pillbox is in between the inner and outer surface of the shell, and let's say the shell is a insulator, you would have to add up all the charge that's inside the Gaussian pillbox. So the charge of the insulating shell that's contained inside the Gaussian, and also the charge inside the nested object at the center. Same thing for the nested cylinder. To calculate the charge in an insulator, when you're given the total charge of the insulator, let's say the total charge is Q, you take the total charge Q and multiply it by the volume of the insulator contained in the Gaussian. So for instance, with the dotted line here, I'm not containing all of the insulator, I'm only containing a certain fraction of it, divided by the volume of the Gaussian, of the insulator itself. Let's say the Gaussian pillbox is in this outer shell. I would have to multiply the volume of the insulator contained inside that, that Gaussian divided by the volume of the insulator itself. To find the volume of the insulator itself, you would have to take 4/3 pi r cubed for this outer radius, and then subtract out this donut hole inside the center, so minus 4/3 pi the inner radius cubed. That would be for the volume of the insulator. So what would the volume of the insulator contained in the Gaussian be? Well, it would be 4/3 pi r of the Gaussian cubed minus 4/3 pi of the inner shell, or inner radius here, cubed. Let's say instead of that, they give us the actual charge density. That's actually a little bit easier. If we know what the charge is per unit volume, all you'd have to do is multiply by the volume of the insulator contained within the Gaussian. So for instance, in my picture here, for the sphere, I just multiply by 4/3 pi r of the Gaussian cubed. Easy. If the Gaussian was in the shell, I'd have to multiply it by the quantity, 4/3 pi r of the Gaussian cubed, minus 4/3 pi inner radius cubed, because I have to subtract out that donut hole. Same idea over here for the cylinder. I would take the density times, so let's say this inner cylinder here is an insulator. I would take the density times the volume of the cylinder, which would be pi r squared, times the length. And that r again would be for the Gaussian. If we're talking about for the shell, it would be the density times the quantity, 4/3 pi, or excuse me, rho times the quantity, pi r squared, where r again is the radius of the Gaussian, times the length, minus pi r squared, where r this time is the radius of the cylinder, times the length. And you could do the exact same thing for the shell itself, and you would get a similar answer for that. So it's just a little bit of algebra that you have to do. All right, so now let's figure out what the electric field is at some location. Let's see, we have this Gaussian pillbox that's kind of inside of this insulator here. We have an insulating sphere contained inside an insulating shell. The sphere has a charge of rho positive 2 microcoulombs per cubic meter, and the shell is positive 3 microcoulombs per cubic meter. Well, before I do Gauss's law, I think it might make sense to actually practice calculating what the charge contained is first. So the enclosed charge would be equal to the volume of the sphere times the density of the sphere, the charge density of the sphere. That would be the entire charge on the sphere. Then for the shell, I'm going to have to take the density, the charge density of the shell times the volume of the shell that's inside the Gaussian. So we know what the the charge density is for the sphere, and we know the charge density for the shell. The volume of the sphere is 4/3 pi r cubed, where pi would be where r would be 0.5. That's for the sphere. And for the shell, it's going to be 4 pi 0.8 cubed over 3, because that's how far we're going out to. That's where the Gaussian is, 0.8, minus the inner shell, the inner surface, I should say, inner radius, 4 pi 0.7 cubed over 3, because that's the inner radius. We can go ahead and solve this, and we end up getting around 3.17 times 10 to the negative 6 coulombs. So that was kind of one of the more difficult ones that you could be asked to solve for the charge. You could do something similar for a nested insulator as well, or insulating cylinder. Okay, now let's go ahead and do Gauss's law. We know what the enclosed charge is. So Gauss's law is the closed integral of E dot dA equals Q enclosed over epsilon naught. The area of the Gaussian pillbox is 4 pi r squared. Q enclosed, we've already figured out what that is. So now we can just simply plug into this. R, they're telling us actually what R is. It's 0.8. So plug that in, plug in the permittivity of free space, and we can actually figure out what the E field is at that location. And I got 44,529 newtons per coulomb. Okay, so that would be how you do the remediation SWIC.